In this section, we're going to talk about different types of electron configurations. One of them is called the noble gas notation. This is an abbreviated method for showing electron configurations, and I'm going to show you some examples here. The first example is phosphorus. You'll notice I've already written out its electron configuration. If you add up all of the electrons in the electron configuration, you'll notice it equals 15, which is phosphorus's atomic number. In order to do this noble gas notation, we're going to replace all the inner shells with a noble gas in brackets. The way you do this is to look on your periodic table and find the noble gas that comes before phosphorus. You can go up one row and all the way to the right, and that'll tell you where the noble gases are. The noble gas I see on the periodic table is neon, which has an atomic number of 10. So what I'm going to do is I'm going to highlight the 1s2, 2s2, 2p6. If you add that up, it equals 10. And I'm going to replace that with neon in brackets. That neon represents our noble gas inner core. Inner shells are not as important to chemists as the outer shells. Let's take a look at iron. I've written down its electron configuration for you. And now we need to find out what noble gas comes before iron. So we go up one row on the periodic table and work our way all the way to the right. The noble gas I come up with is argon. That has an atomic number of 18. So I highlight that. 2, 4, 10, 12, 18 if you add them together. So I'm going to replace that with argon in brackets and write down the remaining part, 4s2, 3d6. The next type of electron configuration is called an orbital diagram. Now I show only the highest levels of energy when I do these, and I also know that if it ends in P, then I do the corresponding S. Let's start with sodium. Here's its electron configuration. 1s2, 2s2, 2p6, 3s1. If you add those up, it'll equal 11, which is sodium's atomic number. What I'm going to do is I'm only going to care about the last level of energy, which in this case is 3s. So I write down 3s, and it has one electron in it, so I draw an arrow in that dash. That dash represents one of the orbitals, and there's one electron in it. Let's try sulfur. Here is its electron configuration. Notice if you add up all the electrons, it equals 16, which is sulfur's atomic number. So the last level of energy in sulfur is the 3p4. But as I said above, if it ends in P, you also do the corresponding S. So I'm also going to do the 3s2. So I write out 3s with 2 electrons in it, one spinning up, one spinning down. Don't forget Pauli exclusion's principle. And then I also do the 3p. Now 3p has 3 orbitals, and remember you have to follow Hund's rule, or the stinky bus rule. So the first electron goes there, the second electron goes there, the third electron goes there, and then finally we go back and pair up for our fourth electron. So that's the orbital filling diagram for sulfur. Let's take a look at manganese. Here's our electron configuration. Notice its highest level of energy is 3d5. So we're going to write out the 3d5. Remember that 3d has 5 orbitals, so we write it out as 3d with 1 electron in each of its 5 orbitals.